All right, welcome everyone. My name is Gautam Kamath, and I'm one of the. I'm going to be the host for today's TCS Plus talk. I am joined by other organizers: Clement Kanan and India Day, Ilya Razenstein, Oded Regev, Thomas Vidic, and recently we have two new additions to the team: Salil Schramm and Eric Weingarten. So I just want to remind people that you will be muted by default, but you can ask questions via a number of different means, including the chat, raising your hand, or simply unmuting yourself. I want to, before we begin, mention the next few scheduled talks. This is a kind of odd day for TCS Plus. We're usually on Wednesdays, but so 2 weeks from tomorrow will be the next talk, which will be Ryan O'Donnell talking about new Ramanujan graph constructions. And then another 2 weeks from that, we'll have Jason Lee talking about results on min k-cuts and k-cuts. But without further ado, I want to introduce today's speaker. Today we will be having Hao Huang from Emory University. Hao Huang works on extremal combinatorics, probabilistic algebraic methods, spectral graph theory, structural graph theory, as well as theoretical computer science. And we're very lucky to have him today talking about a really breakthrough result, a problem that has been open for a long time. A lot of people have thought about it, but Hao has come out with the most elegant proof I could imagine of this. So without further ado, Hao, do you want to take it away?
Thanks for the introduction. And it's my great pleasure to give a talk at the TCS Plus seminar. So now I need to share my slide, I guess. Oh. Okay, let me try to do it. Can everyone see this?
Yeah, that looks good to me at least. Yeah.
Mm-hmm. Okay. So today I'm going to talk about a proof of the sensitivity conjecture, a famous open problem in theoretical computer science. And before mentioning what a sensitivity of a boolean function is, so first let me talk a little bit about combinatorics. So we start with the definition of a hypercube graph. So here we define the n-dimensional hypercube graph, q to the n, in the following way. So the vertex of this hypercube graph is just all the n-dimensional binary vectors, 0, 1 to the n. And two vertices are adjacent if and only if they differ in exactly one coordinate. So here are just some examples of one-dimensional hypercube, two-dimensional cube, and three-dimensional cube. So for the one-dimensional cube, so what you do is you just have two vertices. One is 0 and the other is 1, and you put an edge between them because they differ in exactly one coordinate. And for a two-dimensional cube, so the vertices are just 0, 0, 0, 1, 1, 0, and 1, 1. So you put an edge between 0, 0, and 0, 1, and 1, 0. And in total, there are 4 edges. And for example, you don't put an edge between 0, 0, and 1, 1 because they differ in 2 coordinates. And for the three-dimensional cube, it's just the cube that we're all familiar with. So one quick observation is the following. So you can always choose half of the vertices of this n-dimensional hypercube such that the induced subgraph is empty. So for example, in this Q1, Q2, Q3, you can just take all the blue vertices or all the red vertices. So in particular, for any n-dimensional hypercube graph, you can take all the subsets, or you can take all the 0, 1 vectors whose sum of coordinates even, or those vectors whose sum of coordinates odd. So you see if two vectors are adjacent to each other, they differ exactly one coordinate. So you cannot have an odd vector adjacent to another odd vector. Okay, so we have seen the one way to take half of the vertices of the n-dimensional cube such that the induced subgraph is empty. So another way of saying this is you can take half of the vertices such that the induced subgraph has maximum degree equal to 0. So now you may wonder what happens if we take one more vertex. So we know the induced subgraph cannot be empty anymore. It must contain at least one edge. But can we say something about the maximum degree of this induced subgraph? So for instance, if you take all the even vertices, and then you just change one of the odd vertex into, and you put it into your set, then this immediately creates a vertex of degree n. Okay. So, but actually there's a nice way of just taking a different configuration of one more vertex than half of the vertices, such that for the three-dimensional cube, the maximum degree is only 2 instead of 3. And now we can ask a general question. So what happens if you just take one more vertex than half? If n goes to infinity, how can we minimize the maximum degree of this induced subgraph? Does it have to go to infinity, for example? So now let's play with the 4-dimensional and the 3-dimensional and 4-dimensional case and see what happens. So for example, for the 3-dimensional cube, if you want to take more than half, so you have to take at least 5 vertices out of 8. So if you take these red vertices, it indeed gives you an induced path on 5 vertices. And the maximum degree of a path is equal to 2. Okay. Actually, in this example, you can even take 6 vertices, which gives you an induced cycle of length 6. And you can write a program and search all the H5 cases, and you will realize that no matter which 5 vertices you take, there always exists a vertex of degree greater or equal to 2. Now for the 4-dimensional case, so actually from the lower bound in the 3-dimensional case, the lower bound there also applies to the 4-dimensional case. So if you take 9 vertices out of 16, you can always find a vertex of degree at least 2 in the induced subgraph. And now it's not so obvious to see how to pick 9 vertices such that the maximum degree is only 2. So let me show you a way to do it. So you can just take these 9 vertices. Now you can't really see what the induced subgraph looks like. So let me show in the next slide. So the induced subgraph is just a cycle of length 8 together with one isolated vertex. So there exists a nice way of picking 9 vertices out of 16 in the 4-dimensional case such that the maximum degree is only 2. Okay, so for 2-dimensional case, we know the answer is 2. For 3-dimensional case, it's also 2. For 4-dimensional case, it's also 2. So I became curious, so I wrote a program for the 5-dimensional case. So now you have to search for all the 32 to 17 cases, and you look for the induced subgraph, which is the minimum maximum degree. And it turns out that the answer becomes 3. And of course, I cannot do it for the 6-dimensional case, right? 64 to 33 is just too much. So now we can ask this general question. If you let n goes to infinity and you try to minimize this maximum degree, how does this function behave? So what's this function in n? So this problem was first studied by Chung, Furedi, and Graham and Seymour in 1988, at the time when all of them were at the Bell Lab. So they proved 2 results. First of all, there exists a nice way of taking 2 to the n minus 1 plus 1 vertices, such that the maximum degree is square root of n. And moreover, no matter how you pick 2 to the n minus 1 plus 1 vertices, the maximum degree is at least log n, so half times log n here. So let me briefly explain the construction. Okay. So for the construction, so you take 1 to n, so well loss of generality. Sorry, for simplicity, let's just assume the n is a perfect square. Now let's try to partition the elements from 1 to n into square root of n subset. Each contains square root of n elements. Okay, so here I assume n is a perfect square, so this is possible. Now, if you look at the hypercube graph, so the vertices are just 0, 1 binary vectors, so you can think of them as subset of the set 1 to n. And now in the hypercube graph, 2 subsets are adjacent if and only if you can delete one element or add one element to get one from another. So now let me just take all the sets of even cardinality which contains at least one of those fi. Or you take the sets of all the cardinality which does not contain any fi. So by doing this, you can do a little bit of calculation. So by some inclusion exclusion, one can show that either x or the complement of x contains 2 to the n minus 1 plus 1 vertices. And moreover, we can prove that if you look at the induced subgraph on x or the induced subgraph on the complement of x, then both of them has maximum degree square root of n. So let me briefly tell you how to get this square root of n here. So for example, if you take an even set containing some fi, so now you can try to look for its neighbor. So a neighbor of it is an odd set, and which comes from adding an element or removing an element from it. So if you add an element, you get an odd set which still contains the same fi. So you can't have a neighbor like that in X. Now, if you delete a subset, so if you delete an element from this subset, so for example, if your even set already contains two distinct fi, then no matter how you delete a single element, it still contains at least one fi, right? So for those vertices, the degree is 0. But if your even set contains exactly one fi, so you can delete any element from that fi. So that corresponds to square root of n neighbors. Now, if you look at odd set not containing any fi, now you cannot delete, you can only add element. If you delete an element, you get even set not containing any fi, which is not in X. Now, when you add elements, so the best way you can do is you have this odd set missing exactly one element from each of fi. You can add any of those elements back, and you get an even set containing at least one fi. So basically, this square root of n comes from looking at the number of subsets and the size of subset. So you take these two quantities to be equal to minimize this maximum degree. Okay. So for the lower bound, this log n proof, they use a very clever argument of isopair match inequality on the hypercube and some induction, some double counting statements. So since today I'm going to talk about improved lower bound, so I think I will just skip this proof. Okay, so at this moment you may wonder why is this a TCS plus talk, and why there's any significance of this purely combinatorial question about hypercubes. So why do we care about taking one more vertex than half? So because all these problems are related to a famous open problem in theoretical computer science called the sensitivity conjecture. So first of all, let me define what the sensitivity of a Boolean function is. So a Boolean function is just a function that maps n bits of 0, 1 to 0, 1. And so the sensitivity and the block sensitivity are both complexity measures of how sensitive a Boolean function is with respect to changing some coordinates. So first, let me define the sensitivity locally. So you have a Boolean function f, and you have an input x, which is a binary vector. So the local sensitivity of this Boolean function on the input x is just defined as the number of coordinates such that if you change this coordinate, it will change the value of f at x. So here, this notation just means you change the ith coordinate of x. And the sensitivity of the Boolean function f is just equal to the maximum local sensitivity over all the 2 to the n inputs. For example, let me show you if you take the n function in n variables, then the sensitivity is equal to n. So if you look at the all 0 input, then f of this all 0 vector is equal to 0. So if you change one coordinate to 1, then you still get 0. So the local sensitivity of the n function at the all 0 vector is equal to 0. But instead, if you take the all 1 vector, so it outputs 1. And if you change any variable from 1 to 0, then the n function outputs 0. So the sensitivity of the n function n variables is equal to n. That's because, it cannot exceed the number of variables. And on the other hand, it has to be greater or equal to the local sensitivity at the all 1 vector. So now you can similarly prove that the all function also has sensitivity n. So now what's block sensitivity? So once again, we define it locally. So now instead of flipping one coordinate at a time, you're allowed to flip a block of coordinates. So here a block is just a subset of coordinates. So the local block sensitivity on the input x is defined as the maximum number of disjoint subset of the underlying set n, such that, so you fix S, and every time you flip the coordinates in the subset bi, that changes the value of the function f. So once again, you define the block sensitivity to be the maximum local block sensitivity. So now one can immediately see that the block sensitivity of the n function and the all function are both equal to the number of variables. And that's because the block sensitivity is always greater or equal to the sensitivity, since you can always take the blocks to be like single elements. Okay, so we know, for example, the n function has plot sensitivity at least n, but again, it's at most n because it cannot exceed the number of variables. So it has to be exactly equal to n. And the same was for the OR function. Okay, so now after we define these two concepts, the plot sensitivity and the sensitivity. So we might wonder, are they always equal, just like in the AND and OR function? And the answer is no. And there's this nice construction of Rubinstein function. So you can define a function f which sends n squared bits of 0, 1 to 0, 1. So you can think of this as an n by n chessboard. And now for every row, you have a function g. So g, so for this, for example, for the first row, it outputs 1 if and only if you see two consecutive elements equal to 1 and the rest equal to 0. And now between the rows, you just take the OR function. So if one row outputs 1, then the answer is 1. And if all the rows output 0, then the answer is 0. So now you can show actually the following result. So the plot sensitivity of this Boolean function is quadratic in n. However, the sensitivity of this Boolean function is only linear in n. So in other words, the plot sensitivity is roughly square of the sensitivity. So they are not equal, at least not equal in this case. So now let me show you these two results. So the first plot sensitivity is at least quadratic in n. So let's just look at the local plot sensitivity of this Boolean function at the all 0 input. So if everything is 0, then of course in every row it outputs 0, and overall it also outputs 0. Now let me try to change these two coordinates from 0 to 1. Okay, so now if you look at the first row, you see two consecutive ones, and the rest of the entries on this row gives it, they're all 0. So G outputs 1 here. And for the remaining rows, all of them outputs 0, and you see at least 1 somewhere, so it outputs 1. That means if you change these two coordinates at the same time, then this is so basically this is a sensitive block. Now you can, for example, keep these two coordinates as 0 and then change the next two coordinates to 1. Or you can change the next two and so on. So in total, this gives you roughly n squared over 2 disjoint blocks. So this gives you a lower bound. So plot sensitivity is at least roughly n squared over 2. Now, how about the sensitivity of this function? So again, there are two cases this time there are two cases to check. So either you are at an input whose f value is equal to 0 or whose f value is equal to 1. So in the first case, now because we are taking an OR function between the rows, so every row must output 0. And now I'm claiming that there are at most 2 sensitive coordinates on each row. And that's because, so the best you can do is you have a bunch of 0 followed by a 1 and then a bunch of 0. Now if you change this coordinate, you get 2 consecutive 1s and the rest are 0. Or if you change this coordinate, you get 2 consecutive 1s. So this shows these 2 coordinates are sensitive, and that's the best you can do in every row. So okay, so since you know in every row there are at most 2 sensitive coordinates, and there are only n rows in total. So the sensitivity of this Boolean function at x is at most 2n. So it's at most linear. And now if you look at those x which outputs 1, that means there must exist at least one row that outputs 1. Again, let's discuss 2 cases. If there are at least 2 rows that outputs 1, then you can realize that none of this variable is sensitive because you are only allowed to change one variable at this time. So if you only change one variable, that can change at most the output of one row. Okay, and the other row here still outputs 1, and that does not change the value of f. So the sensitivity, the local sensitivity at those inputs are equal to 0. However, if you only have one row that outputs 1, then what you can do is it's possible that every entry of that row is sensitive. But anyway, this row contains only n variables. So the local sensitivity of f is at most n. So if you look at both cases together, that gives the upper bound of the sensitivity of this Boolean function, which is 2 times n. So the Rubinstein function has the sensitivity, which is like square root of the broad sensitivity. Okay, so previously I showed you that the sensitivity is at most the broad sensitivity. And as I said, Rubinstein's function gives an example that the broad sensitivity is quadratic in the sensitivity. So we might wonder how large can the broad sensitivity be? Can it be exponentially large in the sensitivity? And Nisan and Szegedy in 1992 posed the following conjecture known as the sensitivity conjecture. They asked, is it true that for every Boolean function f, you can always bound the broad sensitivity by a polynomial of the sensitivity? In other words, can you find a constant c greater than 0 such that for every Boolean function f, the broad sensitivity of f is at most the sensitivity of f to the power of c? So once again, you might wonder, so why do we even care about the broad sensitivity? So, I mean, the sensitivity of a Boolean function is obviously a very natural measure of the complexity of this Boolean function. But where does this broad sensitivity come from? And it turns out that actually the broad sensitivity is related to a bunch of other complexity measures of Boolean functions. This includes the this decision tree complexity, certificate complexity degree, approximate degree, the classical, randomized, and quantum query complexities. So it turns out that all those complexity measures are polynomially related. So here, when I say two complexity measures are polynomially related, if you can find two positive constants C1 and C2, such that you can bound one complexity measure from above by the other complexity measure to the power of C2 and from below by the other measure to the power of C1. So now and before this result, so the only exception was this sensitivity. So if the sensitivity conjecture is true, then in Scott Aronson's word, then sensitivity will cease to be an outlier and joins this large and happy flock. Okay, so if you are interested in knowing how these things are polynomially related, I strongly recommend you to take a look at this nice survey paper by Hatami, Grokani, and Pankratov in 2011. So there they proved that all these complexity measures, including some others that I did not list here, are polynomially related. And also they discussed some conjectures that are equivalent to the sensitivity conjecture, some others which are stronger than the sensitivity conjecture, and some others which can be implied from the sensitivity conjecture. Okay. So now if you look at, so let me maybe go back one slide to briefly discuss what this degree of this Boolean function is, since we will use that later. So if you have Boolean function, so the degree of this Boolean function is defined just as the degree of the unique real multilinear polynomial that gives you the value of this function f. So for example, if you have the end function in two variables, then you can just take the real polynomial as s1 times s2. That's because s1 times s2 is equal to 1 if and only if both inputs are equal to 1. So the degree of this Boolean function is equal to 2. And if you take the OR function, you can just take s1 plus s2 minus s1 times s2. So that outputs 1 when you have at least one inputs equal to 1. So in general, if you have an n function or an OR function, the degree of this Boolean function is equal to the number of variables. Okay. All right, so if the sensitivity conjecture is true, then it actually can imply the following consequences. So in some sense, we can view the sensitivity as a measure of how smooth a Boolean function is with respect to the Hamming distance. Or you can say this is at one distance because everything is 0, 1. So if you have a low sensitivity function, it just means that the function is more smooth. So computationally, it will tell you that if you have a smooth or low sensitivity function, that's easy to compute in, for example, in the deterministic decision tree model. And algebraically, it just tells you that such function as a real polynomial must have low degrees. So now let me quickly give you a survey of what's known about the sensitivity conjecture in the past. So there are two lines of research. So you can either try to prove an upper bound on the block sensitivity as a function in the sensitivity, or you can try to find an example just like the Rubinstein function that gives you a good separation. So for the upper bound, so Seymour in 1983 showed that the block sensitivity at most roughly 4 to the sensitivity. So the constant here is 4. And Kenny and Kuti in 2004 implies this constant from 4 to E. And then the state of the art was by Ambani, Gao, Mao, Sun, and Zhou, who improved this constant to 2. And regarding the lower bound construction, so everything known so far is quadratic. So if you analyze this Rubinstein function carefully, you get this half as a constant factor. And if you also consider the parity of n, then you get this extra linear term improvement. And there's a slightly different construction by Ambani and Sun in 2011. So they improved this constant from 1/2 to 2/3. But let's just keep in mind that, so previously all the bounds are exponential and all the separations were quadratic. Now, let me mention the reason why I became interested in this problem. And that's because in the same year when Nisan and Szegedy posed this conjecture, Gotsman-Linial observed this surprising connection with the combinatorial problem I mentioned in the very beginning of this talk. So it turns out that if you can prove that, so if you take an n-dimensional hypercube and you look at the so-called unbalanced partition of the vertex set, unbalanced just means that you cannot partition as half-half. Then, so this is partition, so it has two subset H and the complement of H. If you look at these two induced subgraph on H and the complement of H, and you look at the maximum degree of these two induced subgraph, if you can show the maximum is greater or equal to a function H in N is the dimension of the cube, then this will give you a lower bound on the sensitivity of the Boolean function as a function in the degree of this Boolean function f. So in other words, if we can prove, let's say some lower bound like n to the c here, even something like n to the 1/100, then immediately implies that the sensitivity of any Boolean function is greater or equal to the degree of this Boolean function to the power of 1/100. And since we already know that the sensitivity is at most the block sensitivity, and the block sensitivity and the degree are polynomially related, so that immediately implies that the sensitivity, block sensitivity, the degree, and many other complexity measures, they're all polynomially related, and that finishes the proof of the sensitivity conjecture. And actually, if we go back to our previous problem, so instead of taking an unbalanced partition, we just take 2 to the n minus 1 plus 1 vertices. So if there, we can show that the maximum degree of the induced subgraph is at least n to the 1/100. Then when you take an unbalanced partition, then one of these two induced subgraph must contain more than half of the vertices. So at least one of them must have maximum degree at least n to the 1/100. And we're also done here. In other words, for the combinatorial problem I've mentioned at the very beginning, if instead of this 1/2 times log n lower bound, we can prove, let's say n to the 1/100 lower bound, that already gives you a proof of the sensitivity conjecture. And if you remember that the lower bound, upper bound there, in some sense, it corresponds to the exponential upper bound of this block sensitivity in the sensitivity, and also this quadratic separation that comes from the Rubinstein function. Okay, so it turns out that we can actually prove a very precise lower bound there. So not only we can prove something like n to the 1/100, we can also show a tight bound. So this is the theorem that I'm going to discuss today. So we prove that for every n-dimensional hypercube, if you take one more vertex than half, then it always contains a vertex of degree at least square root of n. And this bound is sharp. that comes from this construction of taking all the even sets containing some fi and all the sets not containing any fi. And now from the Gotsman-Linial equivalence, we can actually show that for every Boolean function, the sensitivity is just greater or equal to the square root of the degree of this Boolean function. And again, this bound is sharp because you can just take this n of all, or maybe all of n function. So you have square root of n crosses, and each cross has square root of n variables. And I think the sensitivity is roughly square root of n, and the degree is n. But once we have this result, we know that the sensitivity conjecture is true. And now I'm already happy with this sensitivity versus a degree. But if you care about the broad sensitivity versus the sensitivity, so here we can use a result by Nisan and Szegedy in 1992 or improvement of Avisheta in 2013. So the broad sensitivity is at most a quadratic function in the degree. So together with this inequality, we can show that the broad sensitivity is at most a false power in the sensitivity. So recall that all these constructions only gives you a quadratic separation. So it's still not very clear whether it's quadratic or quartic. I believe most people are convinced that it has to be quadratic. All right. So for the remaining time of this talk, so let me discuss the proof. So the proof consists of 3 key ideas. So the first one is, so we like to lower bound the largest degree of the induced subgraph. But instead of the largest degree, we can look at the largest eigenvalue. And so if you open any book on algebraic graph theory, so usually among the first 3 results, you can see an inequality like this. So if you take a graph G with largest eigenvalue lambda 1. So here, so let me first say what an adjacency matrix is. So if you have n vertex graph, you can define an n by n symmetric matrix whose entries are 0 or 1. So you put 1 if these 2 vertices are adjacent, you put 0 otherwise. So we know that every symmetric matrix has real eigenvalues. So you can take the largest eigenvalue, and it turns out that it's always less or equal to the maximum degree of your graph. And the proof of this is very straightforward. So you just take an eigenvector corresponding to the largest eigenvalue lambda 1. Let's assume that Vi is its largest coordinate in absolute value. Then if we multiply lambda 1 with the vector V, you just get the adjacency matrix Ag times V. Now let's take a look at the i's coordinate of this vector. So it's lambda 1 times Vi, so it's also equal to the i's coordinates of this adjacency matrix times V. And now by the definition of adjacency matrix, we know this is equal to the sum of Vj for those j adjacent to I in the graph. And we know every Vj has absolute value bounded from above by Vi, and that at most delta of G vertices adjacent to I. So this, by triangle inequality, this gives the upper bound, which is the maximum degree times the absolute value of Vi. And now this Vi cancels, so you just get the maximum eigenvalue is bounded from above by the maximum degree. Okay, so, and on the other hand, most of this algebraic graph theory textbook does not tell you that this largest eigenvalue is bounded from below by the square root of the maximum degree. And that just follows from, so if you start from let's say a graph, you can delete some edges, then the largest eigenvalue can only go down. So if you keep deleting edges until you only, you do this and you only keep all the edges incident to the vertices of largest degree, then you just get a complete bipartite graph K1T, K1 delta actually. And you can compute the eigenvalues of this star here. So the largest eigenvalue is square root of delta, and you have a bunch of 0 and then minus square root of delta. So this already implies that the largest eigenvalue lambda 1 is greater or equal to the square root of the maximum degree. So it turns out that these 2 quantities are polynomially related. So if we like to show that the largest eigenvalue is at least n to the 1 over 100, we just need to show that the largest eigenvalue is greater or equal to n to the 1 over 100. And the reason that we study the eigenvalue instead of the maximum degree is because in some, well, at least in my understanding, that's because in some sense, the maximum degree is the L infinity norm of the degree sequence. L infinity norm is something which is difficult to analyze if you want to use some algebraic or analytical tool. So it's much easier, for example, if you want to understand a L1 norm of the degree sequence, which is essentially the average degree. However, for our case, the average degree of this 2 to the n-1 plus 1 vertex induced subgraph could be very low. So if you remember the previous example, if you take all the even vertices together with one odd vertex, so you get a star with n edges and a lot of isolated vertices. So using this property, so the eigenvalue of that graph, the largest eigenvalue of that graph is just equal to root n. But if you look at the average degree of that graph, it's something like n over 2 to the n, which is pretty small. So both the maximum degree and the eigenvalues are large in that case. However, the average degree is very low. And so this lambda 1 is actually between the average degree and the largest degree. So, and we hope that maybe, and because of this polynomially relation, so essentially we just need to show a polynomial lower bound in this maximum, on this maximum degree. And there's another reason that we consider the largest eigenvalue instead of the largest degree. And that's because the eigenvalue has this following very nice interlacing property. So there's a theorem, I think in the 18th century by Cauchy. It's called the Cauchy's interlace theorem. Now you take a n by n symmetric matrix A, and B is a principal submatrix of A. And by principal submatrix, I mean, so if you take the first, second, and the seventh row of A, so you're also taking the first, second, and seventh column of A. And then this 3 by 3 submatrix is a principal submatrix of A. So we know both of them are symmetric matrix, and so the eigenvalues are just real numbers. So we can just sort all the eigenvalues in descending order. So let's assume that the eigenvalues are just lambda 1 down to lambda n for A, and mu 1 down to mu m for B. And it turns out that for every I, we have the following inequality. Lambda I is at most lambda, mu I is at most lambda I, and mu I is at least lambda I plus n minus m. It's often very difficult for me to memorize these two inequalities, but the way I can remember this is if you take the i's largest eigenvalue of the small matrix, is at most the i's largest eigenvalue of the big matrix. If you take the j smallest eigenvalue of the small matrix, it's at least the j smallest eigenvalue of the larger matrix. So I mean, for example, if you want to prove this, you just need to prove one of them, right? And for the other, you just take -1 times the matrix A, and it's automatic. So the Cauchy's interlace theorem is a direct corollary of this min-max principle. And there's also a very nice one-page proof by, I think, Stephen Fisk. You can find this on the American Mathematical Monthly. So it's just like 3/4 of a page. And I can already show you one lovely application of this Cauchy's interlace theorem. So we can show that if we have a graph G, and we define the independence number of the graph to be the maximum number of vertices such that they are pairwise non-adjacent. So for example, if you have a complete graph, then the independence number is just equal to 1. And if you have an empty graph, the independence number is n. So we can prove that the independence number of the graph is always bounded from above by the number of non-negative eigenvalues of the adjacency matrix, as also bounded from above by the number of non-positive eigenvalue of the adjacency matrix. I don't want to do the proof here because I don't really have a board to write on. So let me tell you how to do it. It's very simple. So just take the independent set, the largest independent set of size alpha, and that corresponds to an alpha by alpha principal submatrix, which are all 0. So the eigenvalue of that all 0 matrix are all 0, and that already shows you that the alpha's largest eigenvalue of the smaller matrix is 0. So from the Cauchy's interlace theorem, we know that the alpha's largest eigenvalue of the big matrix is non-negative. So that at least alpha non-negative eigenvalues. So, I mean, you can do the same proof and you get the other upper bound. So from this result, you can already prove, for example, some nice combinatorial theorem like the Erdős-Corrado theorem. And there's also another version of Cauchy's interlace theorem. So instead of taking the principal submatrix, you can look at a matrix B, which is equal to P transpose times A times P, where P is something called the orthogonal projection, which satisfies P transpose times P. It's an identity matrix. So from there, you also have the interlacing property, and then you can prove the famous Hoffman bound, again on the independence number, using that version of Cauchy's interlace theorem. So let me say one more thing, like why this is called interlace theorem. And that's because if you take m equals m minus 1, then you have lambda 1 greater or equal to mu1 greater or equal to lambda 2 greater or equal to mu2, and so on. And the eigenvalues interlace nicely. Okay, so since we have this very powerful tool, so why don't we just apply it to our hypercube graph? So recall that we would like to show that no matter how you pick 2 to the n minus 1 plus 1 vertices, then the largest eigenvalue of the induced subgraph is at least, let's say, square root of n. And if you look at the induced subgraph, so its adjacency matrix is exactly the principal submatrix of the adjacency matrix of the hypercube graph. So from Cauchy's interlace theorem, so we know that the largest eigenvalue of H, the induced subgraph, is greater or equal to the 2 to the n minus 1's largest eigenvalue of the n minus 1 dimension, so the n minus 1 n dimensional hypercube graph. And we can actually compute the eigenvalues of q to the n. So there are this n plus 1 distinct eigenvalues. So you have n minus 2, n minus 4, you go all the way down to minus n every time you decrease this number by 2. So that n plus 1 distinct eigenvalues. And the multiplicity of those eigenvalues are just equal to the binomial coefficients. So n has multiplicity n choose 0, and the next one is n choose 1, and so on. So it's not so surprising to check that the total multiplicity is equal to 2 to the n, right? Okay, so now what's the 2 to the n minus 1's largest eigenvalue of this matrix? So depending on the parity of n, we know that this number is either 0 or 1. So okay, so let's see what we want. So we want a lower bound on the maximum degree, and we said we'd like to consider the maximum eigenvalue instead. So this gives us a lower bound on the maximum eigenvalue, which is either 0 or 1. So we immediately show that if we take one more vertex than half, then the induced subgraph has maximum degree at least 0 or 1. So even if we prove a lower bound like 1, it's too trivial, right? Because if you take one more vertex than half, so it's greater than an independence number, then of course you have a vertex adjacent to some other vertices. And yet, if you use the interlacing, we already get the following result for free. So we can show that if you take, instead of 2 to the n minus 1 plus 1 vertices, but you take half plus c times 2 to the n vertices, then the induced subgraph has maximum degree at least constant times root n. So this root n just comes from this binomial coefficients. I'm not saying that this is the best lower bound can prove. I'm just saying that interlacing can already give us some interesting lower bounds. Okay, so it might suggest there's a nice way of using this Cauchy's interlace theorem in a different way, such that we can get a lower bound on this maximum degree. And yes, there is such a nice way to do it. So instead of taking a regular adjacency matrix, so we can take a so-called side adjacency matrix. So what you do is you just take your regular adjacency matrix, and then you keep all the 0 entries, but instead of taking the 1 entries, you put either 1 or minus 1. But you have to make sure that, for example, if you change the ij's entry to minus 1, you also change the ji's entry to minus 1 to make sure that it's a symmetric matrix. Otherwise, the Cauchy's interlace theorem might not be true. Now it turns out that actually for every choice of side adjacency matrix, if you compute its largest eigenvalue, this still gives you a lower bound on the maximum degree of the graph. And the proof is exactly the same as before. So you just take the eigenvector, you take the largest coordinate in absolute value, and then you do the triangle inequality. Actually, in the previous proof, I don't even need to take the absolute values. So I just loaded in that way such that it was the same here. Okay, so now this implies that if we can find a side adjacency matrix of the n-dimensional hypercube graph, such that its 2 to the n minus 1's largest eigenvalue is equal to square root of n, then we can just apply Cauchy's interlace theorem and this lemma, and we are done. So in my paper, because I want to make the length as short as possible, so I just construct the matrix explicitly in this way. But later I'll explain where this comes from. So here I take the matrix, for the one-dimensional cube, I just take its usual adjacency matrix, because if I change the one entries to -1, it doesn't really help, right? It doesn't change the eigenvalues. But starting from the two-dimensional cube, I'm already taking a different matrix. So there's one way to define the adjacency matrix of the cube recursively by just taking the adjacency matrix of a n-1 dimensional cube, and then you put I here and another I here, and then you put another copy of this adjacency matrix. Now instead of taking the same copy, I add a minus sign here for the sign adjacency matrix. Now you can prove by induction that mn squared is equal to n times I. Okay, so the square of this side adjacency matrix is equal to n times the identity matrix, where n is the dimension of the cube. So in other words, you can see that all the eigenvalues of this side adjacency matrix are either square root of n or minus square root of n. But since in this definition, we are not changing the diagonal entries of the adjacency matrix of the cube. So all the diagonal entries remain 0. So the trace of the matrix Mn is equal to 0. So if all the eigenvalues are either root n or minus root n, and the sign, and the trace, which is the sum of those eigenvalues, is equal to 0. So the only possibility is half of the eigenvalues are square root of n, and the other half are minus square root of n. So in particular, the 2 to the n minus 1's largest eigenvalue is equal to square root of n, and we are done here. So now to help you better understand this signing, so I put some graphs here. So this is the one-dimensional cube, so I just keep the sign. And for a two-dimensional cube, I just flip the sign on one of its edge. And that's a three-dimensional cube. So you put this two-dimensional cube on the top, and you put another copy with all the signs flipped on the bottom. And for the vertical edges, you just put the positive sign. And then you just recursively define it. Okay. So that's what I put in the paper, but let me explain a different way to view this. It will also tells you that in some sense, the choice of this side adjacency matrix is unique. So here is an inequality by Hadamard. So he showed that if you take an arbitrary m by m matrix M, it doesn't have to be symmetric, then the absolute value of its determinant is bounded from above by the product of the lengths of the row vectors. And one way to understand this is if you view it geometrically, it just tells you that the volume of some parallelogram is less or equal to the product of its side lengths. In other words, this also implies that it's easy to see from this geometrical interpretation that the equality is achieved if and only if all these vectors are pairwise orthogonal. Okay. Now let's try to recall what we need. We need to find a side adjacency matrix such that the 2 to the n minus 1's largest eigenvalue is at least square root of n. So since this is a side adjacency matrix of Qn, so what's the adjacency matrix of Qn? So you see on every row, there are n ones because every vertex has degree n in the cube. And so if you change the sign to, let's say, -1, it doesn't change the length of that row vector. So every row vector is of length square root of n. Now multiply all these lengths, so you get upper bound, which is square root of n to the power of 2 to the n. And now you need the 2 to the n minus 1's largest eigenvalue to be at least root n. And we know that for a bipartite graph, its eigenvalues are symmetric about 0. So for example, if you have 10 as the eigenvalue, then minus 10 is also an eigenvalue of this adjacency matrix. So when you take a sign adjacency matrix of this bipartite graph, it still preserves this property. So in particular, this tells you that you have roughly 2 to the n minus 1 positive eigenvalues and 2 to the n minus 1 negative eigenvalues. And the smallest positive eigenvalue is at least root n. So all the positive eigenvalues are at least root n. And similarly, all the negative eigenvalues have absolute value at least root n. So if you multiply all the eigenvalues, you get the determinant of this sign adjacency matrix. So it's at least root n to the power of 2 to the n. So now you can see this lower bound and the upper bound, they are the same. So it means that if we really want to prove a square root of n lower bound in this way, we need all the row vectors of this matrix M to be pairwise orthogonal. So it's the same as saying that this M transpose times M is equal to n times the identity matrix. And once you know that this is the properties you need to look for, and the rest is just some simple calculations in linear algebra. So I don't want to talk too much about this, but basically you decompose this into two by two blocks, into these blocks. And B is a side adjacency matrix of n minus 1 cube. C is another side adjacency matrix of the other copy of n minus 1 cube. And K is just a diagonal plus minus 1 matrix that corresponds to the vertical edges connecting these two subcubes. And then if you want this M squared to be equal to n times I, you need to have B squared equals n minus 1 times I, C squared equals n minus 1 times I, and BK plus KC equals 0. So in other words, you need B to be a good signing for the n minus 1 cube, and C is equal to minus K times B times K. That comes from the calculation. And in particular, if you let K equals the identity matrix, so if you put all the positive signs on the vertical edges, then this is exactly the same recursive construction I defined earlier. So you have a copy of the cube, n minus 1 cube, you put all the positive signs on the vertical edges, and then you flip the sign in the bottom cube. Okay. I hope that gives you a satisfying explanation of where this signing comes from. And from this Hadamard's inequality, it's not so hard to see that you really need to take a plus minus 1 matrix. Although for the proof of this lower bound, you can take anything between minus and 1, but if you want to get square root of n, you really need to take just minus 1 and 1. And also this signing is unique in the sense that, so for example, in a graph, if you flip the signs on every edge incident to a fixed vertex, that does not change the spectrum of this adjacency of this graph. So up to that operation, the signing is unique. Okay, so here is this equivalence for Gotsman-Linial, but since I think I'm running out of time, so let me just briefly say where this comes from. So for our purpose, we just need to show that 1 implies 2, and there's an intermediate statement such that you only need to look at the Boolean function of full degree and show that the sensitivity is greater or equal to h of n. So 2 to 3 is, 3 to 2 is obvious, and we just need to prove 1 to 3. And for 1 to 3, you just multiply this Boolean function g with the so-called parity function. So it's minus 1 to the sum of its coordinates. And it turns out that the sensitivity of this g corresponds to this maximum of this maximum degree. And the Boolean function has full degree, basically tells you that this is an unbalanced partition. Okay, so before I finish the talk, so let me mention a couple of research problems. So we already know that if we take just one more vertex than half, then there exists a vertex of degree at least square root of n. Now suppose you want to find a vertex of degree at least n to the 2/3. So what kind of number of vertices do you need here? So I don't even know a good conjecture, a good formulation about this. And the second problem. Now, we know the alpha of G is the independence number of a graph. Now, if you just take alpha vertices, then it's possible that the induced subgraph is empty. So what happens if you take alpha plus 1 vertices? Can you say something about its number of edges, its maximum degree, or maybe the largest eigenvalue? So here you might need to assume that the graph is very symmetric, maybe it's vertex transitive, or maybe even some Cayley graph. So it will be very interesting to see that for which graphs this spectral lower bound is actually tight. And the third problem is actually my favorite problem. It's actually not so well formulated. So, okay, so in some sense, the signing of this adjacency matrix can be viewed as an operation such that it changes the eigenvalues of the hypercube. So if you remember the eigenvalues of this adjacency matrix of the hypercube graph, you have this n, n-2, n-4, all the way to minus n. So it's spread out on this in this interval from minus n to n. Now this signing can be viewed as some kind of operation which compress this eigenvalue so that the positive eigenvalue are all concentrated at square root of n, and the negative eigenvalue are all concentrated at minus square root of n. So can we achieve this compression by you compose a couple of compressions to slowly compress the positive and negative spectrum? In the end, you have this positive and negative spectrum both concentrated at one point. So I think this will be useful for understanding some other problems on the hypercube. And finally, can we show that the broad sensitivity is at most the square of the sensitivity? So we prove a quartic upper bound, but can we improve this to a quadratic upper bound which matches the Rubinstein construction, for example? And I think I should stop here. Now the sensitivity has joined this large and happy flock. Thank you.
Great, thank you very much, Hao. We have time for questions. So if anyone has a question, feel free to either raise your hand, ask via the chat, or unmute yourself. So I actually have a question. I'm curious, like now this is related to all these other complexity measures, but can you think of one any concrete implication that you find personally the most exciting of them?
Well, to be honest, I'm a combinatorialist, and and I don't really actually look at those applications. And yep, so the short answer is I don't actually know.
Sure. Okay.
But let me mention one combinatorial problem that I'm really interested in. I don't even know the answer. So now, the n-dimensional cube is basically the Cartesian product of K2. So the two vertex complete graph. If you take a Cartesian product of the triangles, so the independence number is equal to 3 to the n-1. Now, it turns out that if you just take one more vertex than that, it's possible to have a perfect matching. I mean, induced matching. So how many vertices do you need such that you get some, I don't know, polynomial in n, let's say square root of n, or maybe n to the 1/3. Yeah. Okay.
University of Michigan, go ahead, ask your question.
Hi, along those lines, is there anything known or conjectured about Boolean functions on, say, the integer lattice, like integers to the nth power?
So I think Scott Aronson made some conjecture on his blog, but I'm not so sure if this algebraic method can be applied to that particular problem. I think that's still open. Yeah.
All right, any other questions? There's something in the chat. Let me read this out. Kirk has a naive question, he claims, is it possible to use the sensitivity conjecture results for Boolean functions and say something about other families of functions? So
I haven't tried that, but so I think there are some open problems about monotone Boolean functions. You can probably find that in Puya's survey. So yeah, but I haven't really looked into those problems yet.
Cool. Okay, one last call for further questions. If not, I'm going to take us offline in a second. You can stick around with Hao a bit longer and ask further questions. But I just want to remind people that the next talk is about 2 weeks from now with Ryan O'Donnell speaking on Ramanujan graphs, and 2 weeks after that is Jason Lee about K-cuts and graphs. Thanks a lot for joining us.